Hello everyone, hope you guys are doing really good. Today we are going to have another session on path planning of robotic manipulators. But in this particular session, we will keep our focus on one particular technique called potential field method. Last time, we identified that this planning exercise is actually the process of breaking down the desired movement. Into what? Into discrete set of motions. And in that quest, we will make sure that we satisfy movement constraints and we possibly try to optimize time, energy, or some other aspects of the movement. And in that quest, we have previously seen that what are the basic ingredients of path planning, what is meant by states, actions, plan, the criteria, and if there are certain constraints, how to fulfill those. We have seen the concepts of workspace and configuration space, and we have seen that how we are going to map one over the other. And in that quest, we have also seen quite a few of those examples as well. From basic examples to more refined examples, we have seen quite a few of those. And the basic idea was that before we get into one particular paradigm, we need to identify and wrap our head around the basic concepts. So this is what we have done in the previous lectures. We now know that the workspace is going to be one thing and the configuration space is going to be the other thing. And we know that the obstacles are going to be defined in the workspace. And these obstacles are going to have convex or non-convex polygons. And the manipulator is going to try to find a way from the starting configuration, let it be like QS, and reach to the final configuration, let it be like QF. And if we wish to do that, we have to make sure that the manipulator does not hit any of the obstacles. And in order to do that, we have to map this workspace W onto the configuration space Q so that we can realistically find those configurations which are not hitting any of the obstacles. And you can see that all these obstacles are color-coded in this example, and the same codes are mapped onto the configuration space. For example, this obstacle is mapped right over here and somewhat over here in the configuration space. And similarly, for the other obstacles, like this blue obstacle is being mapped over here, as well as a part of that is appearing over here. So if you have a density of obstacles around the manipulator needs to find a way out of those dense population of obstacles so that it starts from the starting configuration and reaches to the final configuration. And that is, in this particular case, being shown in the configuration space with these blue dots. And these are going to be actually the result of your path planning exercise. And this is what exactly we need out of this exercise. So we want to find a path from initial position to the final position so that the starting configuration or initial configuration is labeled as QS and final configuration is labeled as QF, which is going to account for all the joints in a manipulator. And in that quest, we have to make sure that we develop a sequence of discrete configurations which are not going to hit the obstacles in the workspace. So that is going to be the task, which will appear like a map from starting configuration to the final configuration. And for that, we will explore potential field method today. Initially, I wish to explain the basic idea behind it. So you consider your manipulator to be just a point in the configuration space. And the task is quite simple. And if I may try to draw it, something like you have this space available, workspace. And in that, you have the starting point to be this corner over here. And this is going to be your start. and you wish to ask your manipulator, just like a point in the configuration space, to be shifted to another point in the workspace, which is defined over here as the finish line or final point. Now in that, it can simply move from start position to the final position, but the complexity is that there are obstacles in the workspace. Something like this block is placed over there. So this is an obstacle. Let it be like, in order to make a bit more complexity in it, let's have another obstacle added over here as well. So there is another obstacle placed over here, and you wish to move your manipulator from the starting configuration from this point all the way to the final point without hitting these obstacles. So let me quickly write those labels as well. So these are obstacles, and this is obstacle as well. So this can be number 1, and this can be obstacle 2. And you wish your robot to move from start to the final position. So this is the starting task. So what I'm going to do now is to assign a higher potential to the starting point and a lower potential to the final position. And from the starting point over here all the way to the final point, I'm going to define a potential field, just like the grid that you can see over here. So this is going to allow the manipulator in the configuration space to feel attracted towards the final point over here. So this is going to be just like a potential that you have defined, what I should call an attractive potential. And if I define repulsive potential, which pushes the manipulator away for obstacles, for example, in the example that we drew in the previous slides, there was this obstacle 1 and this was obstacle 2. So if for these two obstacles we define a repulsive potential, obviously this is going to force the manipulator to not climb these hills, and that is going to be defined like a repulsive potential. And then if we can add the two, the attractive potential added with the repulsive potential, that is what is going to produce the resultant potential field. And that would look something like a hole potential, where you have combined the attractive potential as well as the repulsive potentials for the obstacles. And this is exactly what is meant by a potential field. And that is going to allow the manipulator to start from the starting point from a higher potential and reach to the final potential or the lowest potential without climbing the hills and resultantly avoiding the obstacles, obviously. And that is going to allow the robot to achieve the task that was assigned. So this whole exercise is to find the highest and the minimum potentials. But how we are going to make the robot move from the highest potential to the lowest potential? How we are going to achieve that? That's the bigger question. So possibly what we can do, we can have a gradient taken of the whole potential, and then we can ask the robot to descend from the highest potential to the lowest potential along with that gradient. And that would be what we call gradient descent method. Now, in order to achieve that, I will start from the same expression that I have written already. The whole potential, dependent on the configuration of the robot, is going to be equal to the attractive potential, also dependent on Q's, added with the repulsive potential. Now, the task is to find minima. And because it is minima, so I can use the gradient of that. So this gradient operator is applied on U of Q. Now, since you can also realize that we are pursuing the gradient descent, so which means that we are going to go down from the highest potential or the higher potential to the lowest potential. So that's why we are going downwards. So that's why this gradient is going to be with a negative sign, and that when taken, I can take the individual gradients, so that would be minus delta of the attractive potential minus del of the repulsive potential. Now with this realization that when I'm going to do that, I will have in the configuration space the torque experienced by the manipulator, and these torques are going to be observed by the joints. So since you know that these Q's are the same Q's that we defined during the Dennevert-Hartenberg convention, so these are going to be Q1, Q2, all the way to Qn for the N-link manipulator. Now you should also realize that, let me use a different color, that this is going to be, these are the torques which are going to be experienced in the configuration space. Now there is a little problem over there. Because these are the torques experienced in the configuration space, which means that this whole exercise is being expected to be in the configuration space, but actually it is not the case, because you have difficulties when you try to define the obstacles in the configuration space. We have said it already that we generally define these obstacles in the workspace. So that's one of the difficulties. The other difficulty is that there are going to be potentially collisions with the links of the manipulator. We define the link initially in this basic idea, just like a point represented manipulator, but actually the manipulator is going to have the body, it is going to have the links. So that's why there are going to be potential collisions with the obstacles and the links of the manipulator. So that's why we are going to define the potential fields in the workspace. So that's why the negative gradient that we are going to expect is going to be resulting us as a vector of forces in the workspace. So that is going to be another observation that we should make over here. And this observation is that important that I've added these points over here in a separate slide. Initially, we have to define the attractive part of the potential field. And by attractive, we mean that it attracts all the Dennevert-Hartenberg coordinate frames that you have attached to all the joints. But also the condition is that this field must be monotonically increasing function so that you can take the gradient of it later on. And also we should emphasize once again that the potential field is going to be defined in the workspace. So once defined, and once we have made sure that it is monotonically increasing function of distance, we can then expect that this potential field is going to apply a fictitious force on all these frames to push the manipulator to the goal configuration. And obviously, we should expect that there is going to be one goal configuration so that it can be defined as the global minima in the potential field. But the question at this particular stage will be that what is going to be that candidate function which fulfills the condition of being monotonically increasing function? We will try two different candidate functions, and we will try to find out the benefits of those so that we may use them in our actual exercises. So the first candidate function for that can be a conic well potential. So as the name suggests, that you are going to have a cone-like potential field where you have a wider area to start with, and as it gets down, it converges to a point. So you are going to have a goal placed over here. So this is going to be a goal position, and you will allow your manipulator to roll down in a point represented fashion downwards. down the gradient. So that would be one candidate function. And for that, you can write down the expression in this form, that you have the attractive potential. And now, since we have defined that these robots manipulators are going to have multiple or n joints for them, and we have already defined the Dennard-Hartenberg coordinate frames for those, so I can have a subscript I added to that. So the ith joint, for the ith joint, the attractive potential in that configuration is going to be based on the distance between where you're currently housed for that particular frame, the origin of it, for the current configuration Q, minus the origin of the same joint at the final configuration. So the distance between the two is what we are going to try to map like an attractive potential, and that shapes like a cone. So that's why it is called conic well potential. Now, in that particular case, the field grows linearly. Obviously with the distance from the goal. Now the problem with that is that it has got a specific problem of discontinuity, if I may say that. So when this distance becomes equal to 0, then obviously you have a discontinuity at that, and that is when you have the goal position achieved. So I must write down that there is going to be a sorry, let me spell check that. You are going to have a discontinuity at goal. So that is going to be one problem that we wish to resolve later on. So we will see that how we resolve it. And the other thing is that when you take the gradient of that with a negative sign, so this is going to give you an attractive force on the ith joint for that. And that is going to be minus del applied on the attractive potential that we have defined at that particular configuration. And that obviously is going to be when you apply this del operator on the function that we have defined already. So how are we going to compute that gradient? Let's see that in the next slide. Now let's define the goal location. This can be placed, for the sake of simplicity, at 0, 0, 0. Now, what does that mean? It means that you have the x at QF, y at QF, and z at QF all equal to 0. Zero, 0, and 0. And I can do that. Can be done without loss of generality. Now, if I do that, the subsequent computation becomes a bit simpler. So I can have the attractive force computed now for the ith frame at the current configuration to be equal to, when you take the negative of this gradient of the function that we have already defined, the conic well potential, that is going to be OIQ minus OI at QF. Now, when I do that, that would be equal to, when you take the gradient of this distance of the x at Q, not at the QF, squared, plus y at the current configuration squared, added with z at the current configuration squared. So when you do that, obviously you can now use the gradient operator, which is actually a vector of partial derivatives with respect to x, with respect to y, and with respect to z, obviously transposed, and then you have the function itself that we have already written down over here, x squared at q plus y squared at q plus z squared at q. Now with this realization, when you take the partial derivatives, it can simply be obviously x of q erase that. So I have this vector which is going to have x, y at q, and z at q, obviously transposed because the partial derivative vector was also transposed. Then you have 1 over oi at q minus oi at qf. And when you do that, obviously you can realize that this is going to be actually the difference between the positions as well. So this can be written like oi at q minus oi at qf divided by this thing placed over there. So this is going to be the magnitude of this difference. And when you have this difference divided by the magnitude of it, obviously it is going to be a unit vector. So let me write that one down. Actually, this is going to be a unit vector, which is going to point towards the goal. So this is an important realization to have, and if you observe, we defined something similar on this diagram earlier. The second candidate function can be a parabolic well potential. Let's explore it. When defined like an attractive potential, it would be something like for the ith joint for a configuration Q, this would be defined like a quadratic function. The origin of the ith frame, wherever that is in the current configuration, minus the same origin of the ith frame for the final configuration, but now you have squaring of this difference. Now once you have got this, you can obviously, on the basis of the previous practice, that we took the minus of the gradient of this function. So this is going to give you the attractive force on the ith joint. So that is going to be minus delta of u attractive on that joint, and that is going to be minus delta of half zeta I x squared on q plus y squared on for the q plus z squared on that configuration q. So once you do that, you are going to get, once again, this is going to be defined like minus half of zeta I, and then you have this vector of partial derivatives. Let me write it better. partial derivative with respect to y and partial derivative with respect to z coordinate transposed times this function. And once you perform this partial derivatives, this is going to be equal to minus zeta for that particular joint, and then the function is going to result in a vector. This vector transposed, and that actually because we have once again the final configuration where you have the final point defined as like a vector having 3 coordinates. For the final configuration to be equal to 0, 0 and 0 transposed, so that's it. Why it is going to be minus zeta I times OI at the current configuration minus OI at the final configuration. So now this is going to be your attractive force acting on the ith joint for the current configuration Q. And now you can see that it is not defined like a unit vector pointing towards the goal location. But the problem with this function is that it grows unbounded. As you move away from the goal location. So this is going to be one of the problems associated with this approach, but it handles the original problem that we encountered in conic well potential, where you had the discontinuity at the goal location. So it doesn't have that problem, but it has got another problem. Obviously, you can observe that there is a discontinuity problem at goal location for the conic well potential, whereas the parabolic well potential doesn't have that problem. But it has got another problem, that it grows unbounded when away from the goal location. So potentially we can add both of them together, and this is going to give us one hybrid approach, which is going to be potentially helpful. And this is exactly what we're going to explore next. So the scheme is quite simple. If you have the ith frame closer to the workspace goal, then you are going to use parabolic well potential, which we have already defined. But if it is far from the goal location, then you're going to use the conic well potential. And that is going to give you the expression in this structured format. So if you have this distance to be less than the distance that you have defined, so it can be a user-defined D, then it is going to use the parabolic well potential. But if not, then it is going to use the conic well potential. And obviously the benefit would be that since now you have the attractive potential to be continuous everywhere, your workspace forces can be defined everywhere. And that obviously would be when you take the gradient with the negative sign of the potential. And when you do that, obviously these are the two expressions. The only difference is that now you have got the influence of D added in the expressions. So when you have D defined by the user, it is going to automatically resort to the parabolic well related attractive force expression, and if it is not, it is going to resort to the conic well potential in order to get benefit from both of them. I think we have had enough of theoretical discussion. We must do one example to illustrate the process. So we are going to consider a two-link planar manipulator. This kind of manipulator you have seen already. So in the starting configuration, this would look something like this. So I'm going to write that down over here that you have this as the starting configuration for your manipulator. Now, once you have this starting configuration, you can readily see that you have QS written down over here, which indicates that it is the starting configuration. Similarly over here. So in the starting configuration, origin of frame 1 is going to be placed at this joint, and origin of frame number 2 is placed at this point. So now I can write down that the starting configuration would be defined like a vector where you have 0, 0 over here. What does that mean? This would mean that theta 1 is equal to 0 and theta 2 is also equal to 0. So that is indicated like a vector over here. So this corresponds to theta 1 and this corresponds to theta 2. Now, once you have the starting configuration defined, you can simply also wish to see that where you wish your robot to be when it reaches the final configuration. So in that particular sense, you would be interested in finding out QF. And for that, I would like to keep it simple. So I'll say that when robot moves and achieves the final configuration, this is going to be your final scenario. And this indicates quite a simple illustration that you have theta 1 rotated to be 90 degrees. So this is pi by 2. And similarly, you have with this virtual line, you have theta 2 defined. So this is going to be also having a pi by 2 rotation. So with this realization that you have theta 1 and theta 2 defined in the final configuration, you can now write those down. So this is going to be pi by 2 for theta 1 and pi by 2 for theta 2. Now once you have got that, you can obviously write down where your origins are going to be placed. So with this realization that you can now write down O1 at the starting configuration, QS, when you have theta 1, theta 2 both to be equal to 0. So that is going to be equal to another vector. Now at this particular stage, I must also define the link length. So let it be like L1 is equal to 1 to keep it simple, and L2 to be equal to 1 as well. So with that realization that when you have O1 to be located at the starting configuration, obviously you would see how this link length is structured. And since you know that Q1 or theta 1 is equal to 0, so this would mean that you have located at 1 as the x coordinate and 0 as the y coordinate. So I can write that one down as a vector over here. So this is going to be 1 and this is going to be 0. And similarly, I can write down O2 for the starting configuration. And that would be equal to, obviously you can observe from the by inspection that it would be 2, 0. So I can write that one down over here. So this is going to be 2, 0. So 2 for the x coordinate and 0 for the y coordinate. Now similarly for the final configuration as well, you can write down where your O1, origin of frame 1, is going to be structured at QF, and that is going to be also a vector. And similarly, you must write down where the O2 is placed at the final configuration, and that would also be a vector. So let's observe the other diagram over here where you can readily identify where the origin of frame 1 at the final configuration is placed and where O2 is placed in the final configuration. So this O1 goes 1 unit along the y direction. So I can write that one down over here. So this is going to be 0 in the x and 1 in the y, and O2QF is going to be simply as you have observed in this diagram. Here it is O2 at QF. So this is going to be minus 1 in the x direction and 1 in the y direction. So that would be written down over here, minus 1 and 1. So now once you have got these origins, these points indicated in the starting and the final configurations, you can now write down the attractive forces. So in that particular scenario, I can write down, let's make one little division over here. So the F attractive at origin of frame 1 is needed to be known, and F attractive 2 is needed to be known as well. So at this particular stage, I'm going to assume that uh, I'm opting for a parabolic well potential. And why so? I'm going to assume that D is sufficiently large so that the problem of the conic well potential is not encountered or is not experienced when things are going to be undefined or discontinuous uh, at the final goal location. So we are going to try to avoid that. So when D is sufficiently large, it would mean that we are going to resort to the parabolic well potential. So with that realization, I can obviously recall that the F attractive for the ith joint is going to be at a particular configuration is going to be something like minus zeta I, and then you have the difference between OI at Q minus OI at QF. Sorry, the space is quite constrained. So I'm going to use this formula to construct the expression for F attractive 1 and F attractive 2. So that would be, in that sense, equal to, let me use a different color now, that would be equal to minus zeta 1, and then you have O1 at the starting configuration minus O1 at the final configuration. So this would be your expression. And similarly for F attractive 2, you can write down minus zeta 2, and then you have O2 at the starting configuration minus O2 at the final configuration. So once you have that, you can simply write that one down. So this is going to be zeta 1, and then you can see what is going to be O1 minus O1 at QS minus O1 at QF, and that can be written down like a vector. So O1 at QS is placed over here, and O1 at QF is placed over here. So all you have to do is to take these two subtracted from each other. So this is going to give you a very simple, straightforward answer. So this is going to be minus 1 and 1, because the minus sign with zeta 1 is taken inside, so I'm going to change the sign inside in this vector as well. So similarly, for the F attractive 2, this is going to be equal to zeta 2, and then you have another vector, and that I can see somewhere over here. You can see that O2 at QS minus O2 at QF is needed. So O2 at QS is this 2 0, and O2 at QF is minus 1 1. So all you have to do is to take this subtraction, and that is very easily computed. I'll write that one. This is going to be minus 3, and this is going to be 1. Now obviously you can observe that you have found out the attractive forces acting at joint number 1. Let me highlight that. At joint number 1, and attractive force at joint number 2. So this is quite obvious that you are going to experience the attractive forces, and those have been computed using the parabolic well potential. We have defined the attractive field quite reasonably well now. It is time now to define the repulsive field. In order to define the repulsive field, we have a very simple criteria. We must avoid collisions. And that can be done if you have a repulsive force defined in the workspace. And that repulsive force should do like repulsion so that the robot doesn't hit the obstacles, and it should do nothing if it is far from the obstacles. There is going to be a region of influence needed for these forces, repulsive forces, to act. And for that reason, you are going to define that radius of influence, rho naught, for all the obstacles. And that is going to repel the robot if it is nearer to that, and if it should not repel if it is far from it. So that's why the expression would look something like this. Now over here you can see that if you have this rho to be greater than rho naught, which you have defined for the obstacle as a region of influence, then there should not be any repulsive potential. But if it is less than that, then it is going to have obviously this as the repulsive potential, where this rho is going to be the minimum distance which is between that particular point on the manipulator to the workspace obstacles. So this OI corresponding to the DH coordinate frames can be corresponding to joint number 1, 2, 3, and 4, where you have placed these coordinate frames. So this is how you define the repulsive field. But then the challenge is how you're going to define the forces corresponding to this field. And for that, we have to take the gradient of it. So in order to define that repulsive force, that would be F repulsive acting on the ith joint in that configuration Q to be equal to obviously minus del of repulsive potential on that particular joint. So in order to keep it simple, I'll consider this, let it be like written down to keep it simple. Let's define this expression rho for the ith origin of the frame to be having only only acting in the x direction. So if you do that, that would mean that you can have the minus del of u repulsive on that ith joint computed in a very easy fashion. So that would be minus partial derivative corresponding to x, because this is only acting in the x direction, of half eta I 1 over rho corresponding to x minus 1 over rho naught, and that was squared. So that is going to be equal to minus eta, and then you have 1 over rho x minus 1 over, let me clean it up, 1 over rho naught, and then you have once again this partial derivative of 1 over rho x. So when you do that, once again, this is going to be equal to eta I, and you have 1 over rho of x minus 1 over rho naught as it is, and then you have obviously rho x raised to power minus 2, and then obviously you have once again partial derivative of rho of x once again. So this would mean that you have now the structure of how this repulsive force is going to be constructed, and that is, in this particular scenario, F repulsive, and let it be defined with X direction only, in that configuration to be equal to minus del U repulsive on the ith joint, for that configuration to be like this. So then you can have this expression rewritten in a general form, like you have F repulsive on the ith joint to be equal to eta I. You have 1 over rho, and then you can have, rather than as a function of x, you can write down like that was in the original scenario, OI at Q, and then you have minus 1 over rho naught, and then you have this thing defined as 1 over rho of OI at Q squared, just to correspond to this term over here, and then you have this remaining term, which you can rewrite as the gradient of rho at OI at Q. So this is going to be your generic expression. We have kept it simple in order to derive it, but once we have derived, we can further upgrade it to fit well with the general case when you have x, y, and z, all the influences added in it. So this is your expression for the repulsive field when you have the robot very close to the region of influence, or within the region of influence of the obstacle, and that is what we will consider while computing in one of the examples later on. And now you can define the whole expression. Whenever you have rho to be less than the region of influence or radius of influence, then obviously that particular obstacle is going to have an influence, a repulsive force acting on the nearest joint or nearest frame. And if it is greater than that, then obviously there is not going to be any influence added on the robot. So for that reason, you can see that this is quite simple in expression, but the only thing that you must take some sort of engineering decision is corresponding to this part of the expression. And this is obviously, you can choose any of the expressions for that, but in order to keep it simple, we can define it like this, that this is just like a unit vector which is pointing or giving you the direction of the repulsive force, and that is what you can use. And in that there is this a B indicated, which is going to be the point on the obstacle which is closest to the ith origin, ith frame. So you can use that. I'll further elaborate that in the example that we have prepared for this particular repulsive field. So we will see that later on. But at this particular stage, this is sufficient to say that this is all you require in order to define a repulsive field. And when taken the gradient of that, this is how the repulsive force is going to be acting on the manipulator. Now we will continue the same example that we introduced initially for the attractive potentials, and that is a two-link planar manipulator. So what we have to do is to find repulsive forces over here when you have an obstacle in the vicinity of the manipulator. So this is the obstacle, which is having an influence on the manipulator. But now that influence is defined by rho naught, and let it be like defined to be equal to 1. So it means that this obstacle is going to have, corresponding to the vertices, obviously, a rho naught to be equal to 1 as a region of influence. So if I just assume that this is corresponding to the scale that we have chosen, so this is going to be this circle around point B that is going to have an influence, a radius of influence over there. So it would mean that O1 will not feel repulsed. But O2 would definitely feel repulsive force, and that's why we have to find out that. So my expectation is that when I keep the rho naught to be equal to 1, I'll just need O2 to be the repulsive force on O2 to be computed, and that would be it. Now, before I proceed with that, I have to define how this point B is located. So this point B can be defined as having a vector in the, because it is a planar case, so it is in the along the x direction 2, and it is along the y direction 0.5. I can assume that. And that would be your vector B. And now I can also somewhere over here recall that what is going to be the F repulsive expression. So this is defined in a very simple, straightforward fashion to be eta I, and then you have 1 over rho for corresponding O minus 1 over rho naught, and then you have obviously 1 over rho for that O squared, and then obviously you have the gradient of rho at for that particular frame. And in that particular sense, you know that the del of rho at OIQ was defined in order to keep it simple, like OI at Q minus B over the magnitude of this difference. So this is going to be OI at Q minus B. So what I can do in that particular sense, that I can compute this first, and then I can plug that in over here to find the repulsive force. So let's quickly do that. So in that particular scenario, the rho of delta gradient of the rho is going to be corresponding to O2, because that's what I'm going to be more concerned about, but because it is the starting configuration, so that's why I'm writing down QS over here, because you can see that the robot is currently parked in the starting configuration. So at this particular initial instance, I'm computing this repulsive force. So this is going to be equal to, now I need O2 at QS minus B. So let it be like written down where this O2 is, and O2 I've already computed. This was 2 and 0, and obviously you can see that because L1 is equal to 1 and L2 is also equal to 1, so this O2 at this particular point is obviously 2 units along X and 0 units along Y. So that's why it is 2 0 minus B can be written down. So this is 2 and 0.5. So this is your numerator divided by the magnitude of it. So this is going to be 2 minus 2 squared plus 0 minus 0.5 squared. So this is going to be 0.5 squared under root, and that obviously is equal to 0.5. So this can be rewritten like 1 over 0.5 into this vector, which is 0 and minus 0.5. So if I do that, this is going to be a vector which is 0 and minus 1. So this is your gradient of rho for O2. And once you have done that, you have computed that, you can obviously put this value in the F repulsive expression that you have written down over here. So let's quickly do that. This would mean that F repulsive on joint number 2 at the starting configuration is going to be equal to eta 2, and for the zeta and eta, this is going to give the user or the programmer the tools to adjust the values, obviously. So this is just like a design tool available to the designers. So I'll keep it as it is, and then you have uh, 1 over rho OI to be computed, which is already done, which is 1 over 0.5 minus 1 over rho naught. Rho naught is 1, so that is actually equal to 1. And then 1 over rho squared, so this is going to be 0.5 squared over here. And then you have obviously this gradient computed already. So this is going to be added like a vector 0 and minus 1 away. So once you do that, this is going to be something like this, that you have eta 2, and then you have this computed to be, let me do one more step over here. So this is going to be 1 over 0.5 minus 1 into 1 over 0.25. Then you have 0 and minus 1. And this turns out to be eta 2. And then you have 0 and minus 4. So this is going to be F repulsive force acting on joint number 2 at the starting configuration, obviously. And also similarly, you can have the F repulsive computed on joint number 1, and because we have already drawn the radius of influence, so that is on the starting configuration to be eta 1, and then you have 0 and 0. So this is how you're going to compute the repulsive force acting on the manipulator when you have one particular obstacle in the vicinity of the robot. And now when I combine everything together, I can readily identify that the workspace attractive force on origin O1 is going to be this expression that we computed earlier, and the attractive force on O2 is computed like this, where zeta 1, zeta 2 can be selected by the user. And similarly for the repulsive force on O1 and O2, these are just computed in the previous slide, and these are the two vectors. So now you have got the realization that when the robot corresponding to especially the n Dennewert-Hartenberg coordinate frames, it is going to experience the attractive and repulsive forces as defined in these vectors, and these are exactly what is going to govern, or what is going to force the robot to move in a specific fashion. And that is exactly what is the crux of the potential field method. So as far as the core of this potential field method is concerned, this is pretty much all of it. Only a few little points are remaining, which we will discuss later on, but at this particular stage, you know how the potential fields are structured, the attractive potentials as well as the repulsive potentials. And for attractive potentials, how to find out the attractive forces acting on the manipulator. You now know the procedure. And similarly for the repulsive forces, you know the procedure as well. So I think you can handle any similar exercise on your own now. A few points will be discussed later on, but that would be the next part. So until then, bye-bye.